Alright, so welcome to part 3 of your Lab 6 videos. So in this video, I'm going to be talking more about individual circuit components. So resistors, capacitors, inductors, all of that stuff, and in the physical realm, what we're actually doing with these. Alright, so first up, let's talk about resistors. We've talked about these guys a lot before, and we've talked about the color codes and all of that. So this is just a basic resistor. And just as a refresher, this guy here, this is our resistor color code chart. So we generally have 3 stripes of interest. First stripe tells us the numeric value of the first digit. So this resistor here is a green, blue, brown. So the first stripe tells us it's a 5. Second stripe is blue. That gives us our second digit. So it's 5, 6. And then we're going to have times 10 raised to the power of the third stripe. So our third stripe is brown. So we have 5, 6 times 10 raised to the first, which means this is a 560 ohm resistor. All right, so that math is important to be able to do pretty quickly. And always remember this order, right? We've got brown, black, and then it's basically the order of the rainbow, right? Red, orange, yellow, green, blue, violet. Of course, they don't have a difference between indigo and violet like we do in the rainbow, because those are virtually the same color. White and gold and silver are, so white is also used. It's the 9th. I don't think I've ever seen it, but it's apparently used. And then we also have tolerance. Almost all of our resistors will be gold. You'll just have a gold stripe on the end, which means they are accurate to 5%. They may be off by 5%. All right, so that is very, very basics of our resistors. Now, what about some other things with them? They also have a maximum power that they can take. So, looking at this guy, this is the pretty much what all the resistors that we will use will look like. These are half-watt resistors. Okay, so that means they have a maximum power dissipation of half a watt. There are some smaller resistors. I may have one on me. It doesn't look like I do. There are also some quarter watt resistors, which are smaller. They can only take a quarter watt of power. But let's work with this half watt resistor. So I'm just going to hook up this one resistor. Now, what happens if we drive too much power through it? Right? So we can solve pretty quickly for what voltage we would need to put through this resistor to achieve a half watt of power. Right? We know our power calculation is going to be V squared over R. So if we want 1/2 to equal V squared over R, we just calculated this as 560 ohms. Right? Now we can solve for what the maximum voltage will be on just this resistor alone. All right, so we've got 1/2. We're going to multiply it by 560 and take the square root of that value, which tells us that our maximum voltage is 16.73 volts on this resistor. Now that's a little high, but it's well within the limits of what we have. We can do 10 volt or 25 plus to minus 25 volts over here, which, because we can do plus or minus 25, if we do both plus and minus 25, that means we can actually do up to 50 volts with this power supply over here. All right, so we could easily go way too high on this resistor. And what happens if you do that? Well, it's not going to explode, I'll tell you that. Generally, your resistor will burn. It doesn't happen right away, and it doesn't just catch fire. But let's take a look at this. So I am going to run too much power through this resistor. I would advise against doing this because it's dangerous. It's bad for your resistors. It breaks them permanently. But this is an educational moment, and we can do that. Okay. So I'm going to hook up my resistor to our voltage. Now, let's go right up to our limit, which was 16.73 volts. Okay, so I'll turn this on the plus 25. and well, 17 volts. That's just about close enough. So this is just a little over our power rating for this resistor. Obviously nothing's happening yet. So you really won't see anything, unfortunately. But if you touch it, ow, it's really hot. That might have just burned me. So that's why we have to watch out for overvolting and overpowering our resistors. Now, if I go higher, we can actually burn this resistor, which will break it. So you likely won't see anything, but you may smell it. You may see a little bit of smoke. It'll get really hot, so I'm not going to touch it now because that will burn me. You may smell it. I probably won't because I'm wearing a mask. But there are things to watch out for when you're doing these labs. So one thing, if you're working with low resistance resistors and high voltage sources, you can worry about burning your resistors, which can be bad. Obviously, you don't want to burn anything. I can actually see that is burning. If you look very closely, it is darkening a bit. You likely can't see that on the camera, but the resistor is darkening and turning black. I can no longer tell the difference between the brown and the black stripes on that resistor because the resistor has darkened so much. So let's turn off this. Let's stop overpowering it, and let's give it a minute to cool off. Okay, this is cooled off a bit. I can touch it again, and I'll try. I don't know if you'll be able to see this with this camera. I'll try and show. You can see a little bit. It's blackened, and it's harder to tell the difference between those two stripes, right? So what else happens? So we can see that it blackened like that. We could obviously feel it because when we are overvolting this, when we're putting too much power through this, it gets really hot to the touch. You could smell it if something's going wrong, and we can also measure it, typically. If a resistor is burned, I mentioned it is broken. You can't use it anymore. What does that mean? Let's measure it and see what happened when we burnt this resistor. Well, actually, it looks like this guy stayed pretty close to its anticipated voltage, or resistance. It looks like it's still just about 560 ohms, which is impressive. Usually, they will change their resistance a lot. Now, I didn't burn this for a long time. I did just kind of let it sit. Regardless, I am going to throw this resistor out because I don't want to be using it now that it is burnt. I didn't severely burn it. If you do a really severe job, what will happen is its resistance will skyrocket. It will look like an open source. It's just open and have just, a theoretically infinite resistance. Clearly, this one didn't burn enough, but sorry for not breaking my things enough. Now, in addition to resistors, we also have potentiometers, which we discussed in our resistive sensor lab. So potentiometers can look like a couple different things. This guy here, I'll put it over on this camera, is a potentiometer. It's got a little screw terminal on the top, and it has 3 legs on the bottom. We have a lot of different forms of potentiometers. This one is also a potentiometer that looks very different. Some potentiometers, they just look different. I don't know exactly why. They just have lots of different formats for them. And finally, this is yet a different type of potentiometer. So the reason all of these potentiometers, they have 3 terminals, that is because when the way a potentiometer works is you basically have a really long resistor, right? And you have a physical sweeper arm that can move along that resistor. And now resistance is a function of both the volume of a material and the inherent resistance of it. So if we can move that sweeper arm along this resistive material, we can essentially change the length of the path between one end and that sweeper arm, that leg that moves along the resistor, right? And so what that does is that decreases the effective volume of that resistor that we are using and changes our resistance. That's how a potentiometer works. Now the two outside legs, they are constant, right? They are not connected to the sweeper leg or sweeper arm at all. So if you use those two outside legs, you just have a constant resistor. Now, potentiometers are going to have a resistance number. This one does not have a visible one. Let's use this guy. Actually, that one's not super interesting. And I just dropped it and it's gone forever. This potentiometer here, is this also not marked? Well, if it's not marked, we can always test it. So the way we'll test, so potentiometers are typically marked with their maximum resistance. That means that they can be usually anywhere from 0 ohms all the way up to that maximum resistance. Now, of course, it won't be exactly 0 ohms or exactly the maximum resistance because nothing is perfect in any of our labs. So if we want to test this potentiometer, we're just going to measure the resistance across the two outside legs. That'll tell you the maximum value of this resistor. So let's turn on our multimeter. Just like before, I've just connected two hanging wires to make it easier to connect my multimeter here. I can clip it on like so. And it looks like this guy is a 10k ohm resistor, a 10k ohm potentiometer. Okay, so its maximum voltage is 10 kilo ohms. And I want to see if we can get both this. Okay, great. Now if I move one of these so that it's on the middle node, now we're measuring the resistance from one end to the middle node. And so this is our variable resistance with the potentiometer. So this guy, you need a screwdriver to mess with. That's why it's got the screw terminal on top. So watch this value as I turn the terminal. So that's dropping as I turn it counterclockwise. It's going to go all the way down to 0.5 ohms. That's super, super small. Now as I go the other way, it's going to rise. So now I'm turning it clockwise up to 10.5 kilo ohms. And we can be any value in between, right? So these potentiometers are super useful if you need a really specific resistor, right? If I needed a 3 kilo ohm resistor, that's not a super common thing to find. So I could use my potentiometer and set it to just about 3 kilo ohms. You have to be careful. It's very sensitive with these screw terminals. All right, we'll call that close enough. They're also useful for calibrating things. So you can use your variable resistor to change its value without changing up your circuit. I'm not going to burn this potentiometer because they are a little more expensive than just resistors, and I'd like to keep this one in operation. All right, so next up, let's talk about capacitors. So we've talked about capacitors before in class, and so I won't get into the physics of it too much, but it is important to understand how capacitors work. So we have talked before that capacitors store charge, right? And they do this by essentially trapping electrons. As current flows, current is a measurement of the movement of electrons. Now, so as current is flowing, that means electrons are moving and they get trapped on one of our capacitor plates. A capacitor is two parallel metal plates right next to each other that are separated either by air or some non-conductive material. So two parallel metal plates. The electrons, in order to move through the capacitor, in order to have current through the capacitor, they need to jump from one plate to the other. And once they do that, they basically get stuck on the plate that they land on. And so what's happening is our capacitor is trapping more and more electrons on it. And electrons are negatively charged. So what that means is now we have a voltage difference. We have a charge difference between two plates of our capacitor. And then when we shut our source off, we still have that voltage difference. We still have that charge difference. And the charge will try to equalize. It tries to become neutral. So that means that the electrons are going to start moving off that plate in the reverse direction. Because we have a negative charged plate, they're going to move away from the other negatively charged things. So the negative charged plate is the plate that they jumped to. They're now going to jump back, basically, which causes current to flow in the reverse direction. So this is effectively storing power, storing charge in the electric field. The electric field is what occurs when we have that charge difference between two particles, or between two things. To show you this, there are a lot of examples on Google. Here's a pretty decent one, right? We can see these parallel plates. You can see the negatively charged plate is down here, right? And then, of course, the negative charges are going to move into the positive zone. Or you can think of it the other way. The positive charges will move to the negative zone to try and equalize that charge difference. Right? There's lots of diagrams of these capacitors here, but the main takeaway is to remember that capacitors store charge in the electric plane by gathering electrons. Now, the reason we see higher resistance over time, we saw that after a long period of time, a capacitor acts like an open, that's like it's gaining resistance over time, is because essentially the capacitor fills up. It's out of space for more electrons. So no more electrons can bridge that gap in between the two parallel plates, which means it's now acting as an open, and we can't make that jump anymore. Okay, so I hope that makes a little bit of sense. Capacitors can definitely be complicated. Now, remember, capacitors, they are resisting a change in voltage, right? They are trapping electrons. They're getting them stuck in there. So they are resisting that changing voltage. However, they don't affect the current. Current flows through a capacitor just fine. So what that means is when we look at a signal, an AC signal, through a capacitor, what we'll see is that current will lead voltage. What do I mean by that? I mean current will be ahead of voltage by 90 degrees, right? Because that voltage is being resisted, the capacitor is stopping it from moving, stopping it from changing. It takes 90 degrees for it to be fully realized, right? There is a little mnemonic for this. It's Eli the Iceman, which I know is a little silly, but so it's not a perfect mnemonic because Eli, the E in this case, is standing for voltage, I guess because there's an E at the end of it. So Eli tells us that there's an L in that, so it's for an inductor, because the symbol for inductance is L. So we have ELI. That says voltage leads the current, because E is before the I in Eli. And then the Iceman, that has a C, so it's for our capacitors. And we have ICE, the I is first, so current leads voltage. I know that's not a great mnemonic, but it's the best one we've got for this. So yeah, you can remember Eli the Iceman, which tells us that in capacitors the current leads voltage. Or you can just remember that a capacitor is resisting a change in voltage. Okay? So what kind of capacitors do we have? There are three main kinds of capacitors. Probably the most common are called electrolytic capacitors. Now, these look like this. They're like a little barrel. These guys there's a couple of very important things. First of all, electrolytic capacitors are typically larger values. So this one here should have it marked is 220 microfarads, which is pretty big for a capacitor. All right? And the way that they work is they actually only have one metal plate inside, and then they have an electrolyte solution, which is used as sort of that trap that we were talking about, where the electrons get stuck in our capacitor. The other important thing with electrolytic capacitors is that these are polarized, right? So that means that one side should be negative and one side should be positive if we are using DC signals. AC, we don't really care. There's no real concept of what is positive and negative because they're constantly switching. But DC, we have to make sure to wire this correctly. So if you look really closely, there's this little stripe on one of the sides. There's no stripe on this side. There's a stripe on this side. That means that's the negative side. Okay, so make sure when you're wiring this, put the negative side on the negative side. If you don't, you'll break a capacitor, which there are certainly worse things, but, then you're out one capacitor. So definitely remember that with these electrolytic capacitors, that they're polarized, and we should wire it correctly when we are dealing with DC signals. AC, again, we don't care because it doesn't really make a difference. So, what happens if I wire this wrong? Time to break more stuff for you guys. So, I am going to plug in our voltage source, our DC voltage source here. Let's wire it correctly first. So if we go the correct direction, I'm actually going to get a resistor as well. It's important to put a resistor in series with a capacitor because the capacitor initially has a 0 resistance, right? So we could, potentially we could drive infinite voltage or infinite current through this because of our initial 0 resistance. So I'm just putting a small resistor there just to limit that current a bit. And this is wired correctly here, but I think my output is still really high, so let's make sure to turn that down. Okay. Much more reasonable voltage here. And, this is going to be just the normal charging behavior of a capacitor. We can leave this and totally forget about it, and nothing bad will happen unless we are sending too much power through this resistor, where I already showed you what will happen there. Okay, now time to mess it up. So I have done this once before by accident. It is not terrible at all if you accidentally wire your capacitor backwards. It's a thing to watch out for, but it does happen. Now, if I do this, at first you won't notice much, but essentially what is going to happen is that capacitor will begin to puff up, and eventually it'll burst. So they are built to burst. There is the top of it basically is breakaway, and it'll spray that electrolyte solution out when that happens. So it can make a little pop. It can be a little frightening. Let's see if I can get it to go here. Well, he's not doing it here. I may leave that for a second and just see if it goes anywhere. I know it's going to surprise me and scare me if I get close to it. Of course, it's not dangerous to get close to it. It's basically water. If the solution sprays on you, I have had it spray on me before. It is not a dangerous solution. It's totally fine. It's basically salt water. So that is fine. Nothing to worry about there. The main worry, of course, is that you're going to break a capacitor and maybe scare some people. But that's it. It may just be stubborn, and it may be that. Let's see, 1 second. Okay, I'm going to try this again with a smaller capacitor, which I think may be easier to pop. Oh, that guy's really hot. That may be because that may be because I was running it backwards. It may also be because I was doing too much power, although the resistor is pretty cool, but I did leave the resistor for a while. let's grab a smaller capacitor and see. This guy is down to 1 microfarad. Still electrolytic, so it is still polarized. And let's drop it in here. Now I should probably be cautious because I am using only a 100 ohm resistor. I don't want to burn that. Let's actually switch that guy out with something a bit bigger. Don't want to go all the way up to a 100K resistor. That's pretty big and will drive no current through our capacitor. There we go. Of course, the resistor doesn't matter terribly much because our capacitor is going to move very quickly to become an open, and no real current is going to be driving through it. Now, there is one small danger with resistors, or with capacitors, that I forgot to mention earlier. So capacitors store charge, right? And as we saw, they will later discharge that. So what can happen is if you charge up a capacitor and then take it out of your circuit, it still has that charge, right? It will still be charged. And so if you then touch it, you make that connection between the two ends, it will discharge through you and it can give you a little shock. If they're really big resistors or capacitors, they can hold that charge for a long time. Sorry, the capacitor was making a noise. I thought it was about to go. So remember, don't do what I'm doing. This is wired backwards and is bad. You can actually see on our voltage supply, it is actually running 0 amps through it, which makes sense because this capacitor is not made to go backwards like this. So, yeah. Now, I know people certainly have used capacitors to play pranks before. If you've got a really big capacitor like this guy, which is 470 microfarads. It's really big. It'll store charge for a long time on its own. You could charge it up and just leave it somewhere, and someone could come along and touch it, and they get just a small shock. I also heard a story of someone who quickly swapped out a capacitor from their circuit, and they just put in their mouth to hold it, and it shocked them really bad when they did that because they just pulled it right out of a circuit. Now, I'm going to leave that capacitor while I go on to talk about inductors. It is making me a little nervous because I know it is going to pop probably eventually, although it may just decide not to today. Let's talk about a couple other types of capacitors. So, electrolytic are very common. We also have ceramic capacitors, which look like this. Oh, you can't see that. Look like this. These guys are not polarized. They are made with ceramic plates. They're made with metal plates with a ceramic disc that separates them. And you don't need to worry about polarizing these guys. They are generally picofarads to microfarads, and they're relatively low voltage values. And then finally we have film capacitors or film canister capacitors, which will either look like they look pretty similar to resistors actually, or the one that I have is this tiny guy, which I believe is also a film capacitor, although this may be a ceramic. I think this is film because the ceramic ones are typically a circle. So these are the most common type of capacitors. These are 5 picofarads to 100 microfarads, and they are fairly reliable. So they have a pretty good tolerance, and they stay at that capacitance. And again, these are not polarized. The only polarized capacitors are those electrolytic ones. Those are the only ones we have to worry about. Okay, so that's capacitors for you. Moving on to inductors. Inductors are a little different. They're like backwards capacitors. So inductors, where capacitors are 2 metal plates, inductors are a coil. They're a coil of wire. And the physics behind an inductor is a little bit more complicated. I'm trying to find a good diagram for you guys here to show you how an inductor works. So an inductor, like a capacitor, is used to store charge, but it is a little more complicated and a little more physics-based than what we have with the capacitor. So over here, this is a basic inductor. You can see it's a coil of wire, and as current goes through that wire, as current goes through a coil, it generates a magnetic field. Okay? And that magnetic field is going to be in and around the capacitor, or the inductor, as you can see here. Okay? Now, magnetic fields are weird and complicated, but the important thing is when we have a changing current, it is going to generate a magnetic field. It's going to increase the magnetic field. And then when we have a decreasing magnetic field, that is going to cause a reverse current to be generated back on the line. So what that means is when we apply current to an inductor, initially all of that energy from the current is going to go into creating the magnetic field. And then over time, that magnetic field becomes its full capacity, and current is allowed to continue through the inductor without worrying. And then when we shut off our source, the magnetic field is going to begin to decrease, which is going to induce a reverse current on the inductor. And so effectively, the inductor is able to store energy into the magnetic field. The physics behind that are weird and complicated, and I don't understand them totally. I don't like magnetic fields, but they are important, and they're important to sort of understand. So where we talked about capacitors, they resist a change in voltage. Inductors resist a change in current. All right? So as I mentioned initially, all of the current is going to go into generating the electric field, and none of the current passes through our inductor. And then over time, the magnetic field is fully charged, and all of our current goes through the inductor. Then in the reverse, when we shut off our current, it doesn't go to zero immediately because we still have current coming out of our magnetic field, which is going to be pushing current back as it decreases. Okay? So we cannot have current that changes instantaneously in an inductor. All right? So current will not change instantaneously, whereas in a capacitor, voltage will not change instantaneously. So again, that's really important to note. In a capacitor, voltage, or in an inductor, voltage can change instantaneously, but current cannot. With a capacitor, current can change instantaneously, but voltage cannot. Now, if we go back to our Eli the Iceman, we can see Eli, E-L-I, that's for an inductor. That means voltage leads current, right? Because I is at the end of that word, Eli. And so what we'll see if we measure the current and voltage through an inductor is that the voltage will lead by 90 degrees. And that's exactly what we talked about with the inductor is resisting a change in current. So it's slowing down the phase, it's delaying the phase of that current, and regardless the size of the inductor, it will always be by 90 degrees. Okay? So this guy here, this is an inductor. There's generally only one type of inductor as far as I know. They are much less common than capacitors for a couple reasons. First of all, they're just made less, and people use them less. And anything that you can do with an inductor, you can also do with a capacitor, just in a different sort of setup. And people don't like them, they don't use them as much, and they're not quite as reliable as capacitors. Capacitors have a pretty set capacitance value and a really low series resistance, whereas inductors, generally, their margin of error is much larger, and they have a significant series resistance. So I actually only have 2 inductors, and I don't even know what I've used them for, but they're these guys here. they are marked as 104 inductors. I don't remember the inductor number code because it is a little different than the capacitor or than the resistor one. I generally just look it up. Let's see if I can find a code. It looks like there are also inductor color codes, is what I'm finding online, which is that some inductors will look closer to resistors. But yeah, you'll often see a more barrel-shaped because we always have that coil of wires, right? Let's see. So when we're looking at our inductor color codes, that is going to be the same system as our resistor color codes. However, it is in units of microhenry, whereas resistors are in units of just resistance. So anytime we use a resistor color code, it is typically going to be in microhenry. Okay? Now, it looks like what I can find is showing that these 3-digit codes, like this one, 104, work on a very similar system. So the first digit there is 1, second digit is 0, and of course that is just the first and second digit of our inductor value. And then the third digit is, once again, just what power of 10 do we multiply it by. But this is in units of picofarads. So if this is 100, that would be 10, because 10 times 10 to the 0, so 10 picofarads, right? So now we have 10 times 10 to the 4th, which is 100,000 picofarads, or 100 nanofarads. Okay, I know that can get a bit confusing, and honestly, a lot of the time I will just use an RLC meter to find the inductance of an inductor that I'm using. But I use them so rarely that I pretty much don't have to do that. All right, so that was a look over at some of our basics of lab equipment. The final piece here that you may see are little chips that look like this. They look sort of like a little bug, like a little caterpillar. Now these guys are going to be integrated circuits. They could be an op-amp, which we'll get into later, but we also used a little bit when we made that circuit earlier using a photoresistive sensor. We used an op-amp for that. So one of these little bug chip looking guys, these will be an op-amp, or they could be logic gates. If you're doing Boolean circuits, they could be a lot of different things. So I always suggest when you're looking at this to look up the number on it. So this one here is an LM324. So if I look that up, let's see, LM324, looks like it's an op-amp, and we can find the spec sheet here. Now it's really important to look at what the pinout is, which is these are the pin connections here, where you can see how each op-amp is laid out and how you should wire this circuit when you're actually using it. All right, great. So that was some really broad basics of a lot of our different circuit components and a lot of what we use in lab. I wish you guys could be here. I think these labs in person are really great and very valuable. Now, if you guys are ever interested in doing any of these labs, trying to build some of these circuits or just getting hands-on experience with some circuits, you can talk to some of the TAs. I know some of us are definitely willing to be here during our office hours. I'm definitely willing to be here. If you're interested at all in getting hands-on experience with circuits. I love doing circuits and this kind of stuff, so I'm more than happy if you show an extra interest to be here. Yeah, just let me know. I'm on Discord and all of that, so just shoot me a message if you ever want to come in and take a look at some of these circuits. All right, so for this lab, there's also not really going to be a write-up because you're mostly just watching me explain things, but there will be a Canvas quiz, so do make sure you get that submitted. I'm not totally sure what Checkoffs are going to look like for this lab, but we'll send out an announcement later on Discord. All right, let me know if you have any questions. Thanks.